I'm Phil Karn KA9Q. I'm going to talk about a project I did last year, which was part of the much larger ISEE-3 recovery or reboot project that was led by Dennis Wingo of SkyCorp out in California. Now, you heard something about this last year from Mario at the L5MOL and Occam about the role that the Bochum ground station played. I'm going to talk just about my specific piece of the project so I don't repeat things that you've seen or can get elsewhere. I've sort of gotten somewhat of a reputation, I guess, as an FEC expert, specifically low-speed satellite FEC. And actually, before I even got involved in this project, I had done a number of these things before. It started back in the 1990s when I started writing software decoders for various forward air correction codes, Reed-Solomon, Viterbi, convolutional, and so forth. So I've done both amateur and non-amateur satellites. There were a couple of non-amateur scientific spacecraft, the Advanced Composition Explorer ACE, which was launched in 1997, I believe, Stereo, which was launched in, when was Stereo launched? 2007 or 8 or something like that. Both of these, I was invited by NOAA to implement low-speed decoders for their real-time solar wind data, so they would not be dependent, full-time on the Deep Space Network, which is very costly. And so I ended up doing software demodulators for both of these using the formats and error correction codes that were already defined. As far as I know, the code I wrote way back in 1999 for ACE is still in production use around the world and collecting data. The code I wrote for Stereo was originally using a convolution coder designed for the Cassini mission, and that was run operationally at Bochum for a number of years until they switched over to turbo coding using a turbo decoder that Mario implemented. And within HAM projects, I have done I've designed the coding schemes as well as implemented the decoding software for AO40, which was reused in AO73 on FunCube for the telemetry format, on AeroSat-1, which was launched from the space station in August of 2011. And then more recently, I've designed the low-speed telemetry of the Fox-1 spacecraft, which is yet to be launched. So I kind of have a history of this doing this sort of thing. So the story with ISEE-3 begins in late March when I get this email from Mario saying, "Gee, do you know where we might be able to get a decoder that can do this?" And it's an innocent enough question, so it begins once again. I just can never say no to these kinds of things. Somebody throws a challenge in front of me. So to review what the telemetry looks like, this was a spacecraft that was launched way back in 1978, so this is 1970s technology. This spacecraft had no cameras, so there was no need for high rate telemetry. The highest telemetry speed was, I think it was it was either a kilobit or 2 kilobits per second. I'm not sure was the highest possible data rate. The lowest rate was actually 16 bits per second, as low as it could go. And it used a much older form of convolutional encoding that was designed for an older technique that is now pretty much obsolete called sequential decoding. It was also sometimes known as the Fano algorithm. Other than that, it was a fairly classic deep space design. The RF carrier on S-band was phase modulated with a residual carrier, which makes it very easy to track when there's Doppler or uncertain frequency. The data itself is Manchester encoded on a subcarrier at very low data rates, at the lower data rates, or directly encoded onto using biphase Manchester at the higher data rates, which then phase modulates the main carrier. For a very quick review, it is not a tutorial about convolutional encoding, Viterbi decoding, but just to understand what the nature of the project. A convolutional encoder that's used for error correction includes a shift register, which is, as you see here at the top, the data bits are sequentially clocked in one by one, and then after each new bit is clocked in, a set of fixed taps are XORed together to produce an encoded symbol, and then those symbols are set in sequence. So you clock one data bit in here, and then you send each of these symbols in sequence, and you clock the next bit and so forth. So you can see that as the data bits propagate down this register, they all affect the output until the bits start falling off the end. And the length of this register, K, is known as the constraint length. Because once the bit has fallen off the end, it can no longer affect the output, because the register is a finite length. If you represent the state of this encoder, all possible states that the shift register could be in, you can represent it as a tree, depending on whether you have a 0 or a 1, and you could, explore this tree. This tree assumes that basically the encoder is infinite length, that every bit always influences the output forever. That's one way to model, and in fact, that's how sequential decoding works, is that you're exploring a tree. You walk up this tree, and as long as you seem to be on the right path, you keep going. If you seem to have found that you're on the wrong path because noise made you take a bad turn, you'll back up and you try another one. You'll back up further and keep going until you explore a path that seems to be the right one again. That's how the sequential decoding algorithm works, but it has its problems. It tends to be rather unstable, and it does not always give you the best possible performance. So in the late 1960s, Dr. Andy Viterbi came up with his now very famous algorithm called the Viterbi decoder. The interesting thing about this algorithm is that it works as well as trying all possible data sequences to see which one most closely matches the received data. But it does so in a way that's actually computationally tractable. So it's equivalent to that, but in which case it gives you maximum likelihood decoding. It gives you the answer that is most likely the one that was sent, but it does it in a way that's actually computationally feasible. And the reason this is possible is because of that constraint length being limited that I talked about, that bits fall off the end and can no longer influence the output. So instead of drawing the state as a tree that branches forever, you draw as a trellis. The paths merge when bits fall off the end of the register. And so it's actually very similar to a route finding algorithm. You're trying to find the shortest path between city A and city B. You have all these possible paths, and you can actually apply something very much like the Viterbi algorithm to finding the shortest path to a destination. Now, there are some problems with this. I mean, there are good things and bad things about any algorithm. It doesn't really matter how many bits or how many symbols per bit you send. The complexity is really only weakly dependent on that. However, it's exponential with the constraint length. The longer the constraint length, every time you increase it by 1, the complexity of the decoder doubles. So that means the computational complexity is exponential. And one of Irwin Jacobs, who was Viterbi's partner when they founded Qualcomm, said one of his older papers, a phrase that I like to use a lot, which is, one does not trifle with exponentials. Exponentials grow and grow and grow, and eventually they become unmanageable no matter what kind of technology you have. Now, back in the 1970s, the late 1970s, when this algorithm was actually first used in space, in the Voyager 1 and 2 spacecraft, this value k = 7 was very common. It is a 7-stage shift register. And that's still a code that's actually very, very widespread use. But it turns out that if you increase the length of that, you can do better. You can operate to lower signal noise ratios. And the longest, the code that I know of that's used routinely with Viterbi decoding is a k = 15 code that was originally developed for Cassini. And it was also used in stereo until they switched over to turbo codes some years ago. But the difference in complexity, again, is exponential. Going from 7 to 15 is an increase of 8, which means that the complexity of this decoder is 256 times that of the k = 7 decoder. So now I'm asked, okay, what can you do one for k = 24? Well, let's see, 24 minus 15 is what, 9. 2 to the 9th is 512 times. So it's 512 times as complex as already most complex decoders ever been used in routine use in a deep space project. So Mario's original question was, could I use that decoder? Could I adapt it and make it work to the ISEE-3 code? And to my utter amazement, it worked. All I had to do was change some constants, recompile it, and it actually worked. First time, I couldn't believe it. But sort of. I mean, it only ran at 225 bits per second on a late model i7 CPU, even using the vector instructions, which I used to write all my decoders. And the reason for this is because for every single bit that the decoder decodes, it is reading and writing 16 megabytes of path metrics, and it's writing 1 gigabyte of decisions of every single bit that it is decoding. This is why it's only 225 bits per second. Okay, so actually, I think this is actually pretty good for that kind of complexity. So the challenge here was not to just do it the way it was originally designed. I wanted to do it the way that was completely out of the question back when the spacecraft was first designed. Unfortunately, it still wasn't fast enough. So it was fine for some of the lower data rates, but as the spacecraft got closer to Earth and they upped the data rate because the link budget could support it, there was basically no way I could make it go faster. Additional CPU cores are basically useless because the caches are too small. And all those reads and writes that I just mentioned were blowing out, were overflowing the caches in the CPU and going out and saturating the memory bus. And since all the cores of a CPU, multi-core CPU, are sharing the same memory bus, you don't really get any speed up by trying to use multiple cores. They all just slow down proportionally to the number that you have running. So I ended up eventually, after going through many iterations with this and giving up on trying to make my decoder any faster, I built a hybrid decoder where I try to combine the best of both worlds. I used the old sequential algorithm, which is suboptimal first. If that works, I'm done. Great, it's nice and fast. But if it fails, then I'll fall back and use the Viterbi decoder. But I don't want to do that every time because I might be trying to decode noise, and I'll just fall farther behind trying to decode noise. So I use this heuristic that actually turned out to work very well, which is only at the last frame was successful. Then I'll fall back and try Viterbi. This actually turned out to work very, very well. But it's actually easier said than done to say, have I decoded the frame correctly, because there's no CRC. I don't think this was before CRCs were invented, but for some reason they didn't use one. So I had to use some heuristics to see whether or not the data looked kind of right, to see whether I decoded the frame correctly. So I ended up with a Linux pipeline, a command pipeline I could run in Linux or Mac OS with three components. There was a carrier demodulator, PM demod for demodulating the phase modulation. It had to acquire the residual carrier and take it down to baseband. Then I wrote a second program that took the output, the baseband output. It tracked the symbols at whatever symbol rate was currently in use. Tracked the symbols, found proper symbol phasing, and then sent baseband symbols into this decode program, which actually ran the Fano and Viterbi decoders. Now I have a recording here what this sounds like. Here we go. For some reason, the button doesn't show up when I do full screen, but this is what it sounded like at, I think, 512 bits per second, if this is working. Should be audio here. Well, I've never used this feature before. Oh well, anyway, it was optional. Okay, so it all worked, and I was actually pretty happy with this. And then I found some little interesting, the devil's always in the details. One of the many people out there who were also looking at this data discovered that there was a slight FMing of the carrier along with the Doppler shift that you can see here in the waterfall diagram. There's this very small FMing of the signal, which wasn't mentioned in any of the JPL papers. And the cause of this is still a little uncertain. It's obviously caused by there being a physical offset of the S-band antenna from the spin axis of the spacecraft, so that as it's rotating around, it's coming towards you and away from you and towards you. And I computed it was only a few centimeters, but it was enough to cause about a hertz or so of Doppler on the carrier. And this actually affected me because my tracking bandwidth is only about 1 hertz, so the carrier is being Doppler spread outside of my tracking loop bandwidth, and I found I was actually losing some performance on that, and so by increasing it, everything worked fine. On top of that, there's also some amplitude modulation. It's a spin modulation from the fact that it's an array of 4 antennas as you spin around, so there's about over 2 dB peak to peak of amplitude spin modulation on top of this, which anybody who's ever worked on any of the Phase 3 satellites sounded very, very familiar. That's why I wanted to play the audio, which unfortunately impaired our link budgets by about 2 dB because it wasn't really designed to deal with that fading. So it was a lot like going back and trying to deal with Oscar 40, really. And it's even S-band, too. So I can now say, I think I can claim the operational record for the largest Viterbi decoder that has ever been used in an operational, as opposed to a laboratory test, operationally a real spacecraft in space. And I expect this record to stand for some time because absolutely nobody in their right mind will ever do this again. Now that we have turbo decoding, which actually works better, it gets you closer to the Shannon limit for much less complexity. There's no reason to ever do this again except when working with an ancient spacecraft. And who knows, there may be another ancient spacecraft we'll do this again with soon. I don't know whether that's going to happen or not. But it was a fun project, and I enjoyed it quite. I would definitely do it again, even though the overall recovery project did not succeed because of the lack of pressurizing nitrogen in the propulsion system, I had a blast doing this. It was a lot of fun. I mean, even the outside chance that we would succeed was enough. So every project like this has to have a list of lessons learned at the end. Primary lesson is don't let anybody, especially Mario, ask, can I use your software for something? Because you're going to end up doing the whole thing yourself. You'll just get sucked into this. It's not the first time. It's happened before with these NOAA projects. One lesson I learned, and it doesn't just apply to me, but to I think everybody on the project, especially some of the other guys I was working with, which is that when you have a project like this, and you know that you have a problem and something that you need some help with fixing it, don't wait. As soon as you know you have a problem, put out a call right away for people who might have expertise in a particular field to give you help. Because if you wait, even if the right people come along, they're just not going to have enough time to really fix this. Although we had a lot of fun doing this, Mary and I both felt that we could have probably done quite a bit more. If we had several months of extra warning, we probably could have come up with a really good ranging Doppler range rate system that we could have implemented at Boca, but we simply didn't have the time. And instead, the project had to go off and spend $3,000 an hour to the Deep Space Network to get time on their dishes to try to do that tracking. And something we could have done and probably learned a lot from if we just had advanced warning of a couple extra months. And now, during all of this, in fact, just a few weeks after I got that original email from Mario, I find out that I have phase 4 lymphoma, and I'm going into chemotherapy during all this time. So I'm really concerned, should I really commit to a project like this? I feel fine now, but how am I going to feel? I don't want to commit to something that involves letting people down later. But it turns out it was not nearly as bad as I thought, and having a project like this to keep you busy and keep your mind occupied while going through that was a definite psychological boost. So again, I'm glad I did it, and I had a pretty good time, even though the project itself did not succeed. So here's some links to other things if you really want to dig into this. This is where I have all my source code and the telemetry files that I decoded. If you want more information about the project itself, that's the central link that will tell you everything. And then Valence Sieber, who actually works for Matt Edis, the company, Edis Research is the company that makes the USRP. He has an excellent talk about his part of the project, going to Arecibo, installing USRP radios and getting the data and doing the uplink. I didn't have anything to do with the uplink. I was only working on downlink. He had to figure out the old command sequences, which were some archaic form of FSK, which NASA was not even capable of generating anymore. And if you want the story of how they did that, that's the place to go. So that's it. I wanted to keep this really short and just concentrate on the part of the project that I was personally involved in, because there's a lot of other references for the rest of it. But I had fun doing this. Any questions? I guess I spoke too fast. Okay.
Actually, I have one.
Sure.
Probably not related to this. You talk about 24 constraint length being the longest ever implemented.
That I know of, and used operationally.
But I know it's not decoding with Viterbi, but the WSJT uses 32 constraint lengths. What is the difference in that?
Well, these longer codes were designed for sequential decoding, which was very common back in the 1960s and maybe halfway through the 1970s where Viterbi took over. In those days, Viterbi is completely out of the question for anything longer than, constraint like 7, 8, 9, something like that. So I just took this as a challenge to show how far computers have come since then, that I could take something that would be completely ridiculous in the 70s and 80s and show that I could do it on my laptop. I mean, you really, it's a good demonstration of how far we've come in computing power to be able to do this using an algorithm that was completely out of the question back then.
So WSJT was presumably done in a different way, decoding that?
Well, if it was designed with a long constraint length encoder, then it was obviously intended for sequential decoding, which is suboptimal. It can work well, but that's why it's not used much anymore. So. Yes.
Any chance you could play that audio file?
Oh, yeah, maybe I could actually. Maybe I could. Because I just grabbed it today. I'll have to find it here a second. I have to get my mouse cursor back. I think I have it in my iTunes library here somewhere. Let's see if I can find it. There it is. But I'm still not hearing any audio. I don't know why I'm not hearing any audio. Oops, that's not good. It's working this morning. I think it's muted. No. No, it's not. There we go. There we go. All right. How's it coming through the PA? Is there any audio back there? Was, huh? I mean, I can just play it out of the speaker on my laptop. Anybody hold the mic up next to it, I guess that'll work, yeah. Yeah. Spin modulation is very obvious. I mean, it's very familiar. Anybody who's ever worked AO40. I think that was 512 bits per second, so the symbol rate is 1024, and the frame size would be about every 2 seconds or something like that. Anyway, again, very familiar to those who've ever worked one of the Phase 3 satellites with the spin. Now, of course, you should not be able to hear that, right? I mean, the modulation encoding is designed to work down at signal noise ratios where all you would hear is noise. The only reason it sounds like this is because they're receiving an AMSAT-UK. And they were getting 30 dB signal noise ratios. Okay, they were incredibly strong. Now, so I'm wondering, well, gee, am I wasting my time doing this? And why am I even bothering to, error correct the signal at 30 dB? It turned out it was actually very useful because, well, Mario with his puny little 20-meter dish over in Bochum actually does need this, okay? And it turns out he pulled their fat out of the fire when it came time to do commanding because at Arecibo, apparently they have to do manual TR switching between the transmitter and the receiver. And they had to actually go up in the cab to do that. And it took, I don't know how many seconds to do it. Now, the idea of racing the speed of light by doing something mechanical is a bit mind-boggling to begin with, but it ended up, the only way it was practical to do it was for them to transmit from Arecibo from Mary to receive in Bochum, in a bistatic mode. And it was really the only way they could do any commanding. So we really did, the two of us really, or all the people who worked on this really pulled the fat out of the fire just by having this ready when they needed it. So I kept asking him, do you need anything more from me? Do you, is the decoder enough? Do you have the phase demodulator? Do you have the symbol? Do you have all this stuff? I didn't really hear anything. And they say, well, we've got telemetry, and I'm looking at what they've got. They've got all these fancy spectral plots and oscilloscope diagrams, but the one thing I don't see are bits. So I said, can you please send me one of your raw IQ files? So they send it to me. It's like a gigabyte long or something like that. Sample some incredibly high sample rate. I run it through my code. I get all these frames coming out. I send the frames back to them, and like within 5 seconds, I see it tweeted around the world. They obviously didn't have the telemetry until I gave it to them. So again, this is that old principle. Don't be afraid to ask for help when you need it, and do it as soon as possible if you really want a project like this to have the best chance of succeeding. Anything else? Yeah.
Hi, could you tell us what you would do, for instance, if you had a chance to do the sort of AO40 format, perhaps again?
I'm sorry, you were covered up by feedback there.
Yeah. So if you were going to do the AO40 format again,
Yeah.
what sort of forward error correction would you use now in 2015?
The AO40 problem was constrained by the hardware on AO40. I mean, I could not change the bit rate. I could not change the fact that it was Manchester BPSK. Those were, and I did not want to change the frame size. So those were given. So I was, I designed around that. Now I know it was used for AO73. I guess it's working well. I mean, people seem to like it. I probably could have done a little better had I designed it specifically for AO73. Nowadays, probably the main change I would make in designing a new system is use turbo coding for everything. Turbo coding was only invented in the early 90s. France Telecom had the fundamental patents on it, but they expired in 2013. I don't know about any other ones, but hams are always following the trailing edge. We use something as soon as it's falling out of patent or whatever. But But that's probably the main change I would make. And I can confidently say I don't think there'll be any more breakthroughs in coding beyond turbo coding. When you're within a fraction of a dB of the Shannon limit, that's it. There's nothing else to do. Okay, thank you.
Thank you, Phil. I'm sure it'll not give Phil a round of applause.